Right. All right. Hey, everybody. Thank you for joining in on the Marine Institute Graduate Society seminar series. We meet every week on Wednesdays at noon. This is our second to last seminar, and this is our for the winter 2022 semester. This is being recorded and will be uploaded to our YouTube channel, where you can find almost all of our seminars over the past couple of years. Before we start, we do want to provide a land acknowledgement. We respectfully acknowledge the territory in which we gather as the ancestral homelands of the Beothuk, and the island of Newfoundland as the ancestral homelands of the Mi'kmaq and Beothuk. We would also like to recognize the Inuit, the Nutsiavut, and Nunatuckavut, and the Inuit of Nitassinan and their ancestors as the original peoples of Labrador. We strive for respectful relationships with all the peoples of this province as we search for collective healing and true reconciliation and honor this beautiful land together. Now, please join us in welcoming Dr. David Keith and Ph.D. student Raphael McDonald. Dr. David Keith got his Ph.D. at Dalhousie University in 2014, studying stock recruitment dynamics at low population sizes. Dr. Keith currently works as a research scientist at the Bedford Institute of Oceanography for DFO in Dartmouth, Nova Scotia, where he leads the research program for inshore and offshore scallop fisheries. Dr. Keith is also an adjunct professor at Dalhousie University, where he supervises students. And speaking of, Dr. Keith has PhD student Raphael McDonald here with him to help give today's talk. Raphael started his PhD in statistics this year at Dalhousie University, where he studies stock assessment. Until starting his PhD, Raphael worked at the DFO in Dartmouth, where he helped assess scallop populations using spatial stock assessment, which I'm assuming led beautifully into his PhD. So in short, we have some modeling masters here, and we're lucky to have working in fisheries with us. With that, I'll hand it over to you guys.
Thanks, Colin. Can you hear me okay? I just got a message. I might be a little mumbly. Okay. Cool. Okay. Thanks, everyone, for coming out to see this talk. I'm kind of just going to set Raphael up and let him go off on all the cool modeling stuff he's doing. So that's kind of the plan for this, but I'll provide a high-level overview on what our fishery does and a little background on Scallop. This has been a big collaboration over many years with many different groups. We've listed some here, and there's broader implications to what all this spatial research we've done is as well. But as I say, Raphael's led this component that we'll talk about at this time with help of several other people and many, many other people we're not going to talk about. So background on the sea scallop fishery and sea scallop in the maritime regions is what we'll start with. I'll give you a biological overview because I'm guessing some people don't know a lot about scallop, and then talk about the fishery in the Maritimes. Then move on to our assessments, talk about our model in general and a reformulation of the model that we undertook. Well, I should say Stephen Smith undertook about 7-8 years ago. And what that's led to is essentially the work Raphael's done. And so there's 3 stages to the modeling that he's been doing. The first part is TLM model. It's an integrated assessment. He'll explain in detail what that is. I'll come back around to it a little bit myself. And when we have SEBDAM, which Raph came up with that acronym of Spatially Explicit Biomass Dynamics Assessment Model. So basically, it's taken this TLM model and added spatial component to it. So now we can actually predict biomass in space within an assessed area, which is a really cool new trick we have. And then we'll close off talking about what Raph is working on right now in his PhD, which is adding habitat to the model for the region. So sea scallop, a little biology background, or you guys. This sea scallop, Placopecten magellanensis, if I'm saying that right, I should. This typically found depths less than 110 meters in our region, so kind of shallow. 50 to 80, 50 to 90 is kind of the sweet spot generally in our area. It's a sessile broadcast spawner, separate sexes. And we have this neat thing in scallop, empty paired scallop shells. This actually is really important. We probably don't talk a ton about it in this, but it is a really handy index of mortality. These things are called clappers. So we get a toe in of a whole bunch of scallop, and some of these scallop will be paired shells, but there's actually nothing left in the scallop. It's died recently. And what that gives us is a way to estimate natural mortality that hardly any other fishery really has a very good handle on. So it's a big advantage we have with our assessments. And just note, the fishery lands generally just the scallop meat, and they're not usually this big, but that was a really big one we found on survey a few years ago. So generally just the meat. If you go to Europe, you'll see that they land the whole animal, and you can, they'll sell the whole scallop, gonad, and everything. Whereas here, it's generally just the meat that's landed. Scallop is a generally sedentary species. It can actually get up and swim, the younger ones do get up and swim. We've done video work. Jessica's actually got a paper on it with swimming speeds of younger scallop. So the younger ones will move, but not enough to really matter, at least in terms of what we're talking here. It's not like a fish, obviously, but they can move a little bit. They form beds, so it matters where you live. And they're often found in patches, these beds. Heterogeneity is the rule. So we get beds, and then we get areas where you don't actually see much scallop. And really the bottom type is a big driver of this. And so this is what we're trying to get at now, is the effect of bottom type on our assessments. Generally, I mean, every stock assessment model is averaging across heterogeneity. That's just the way of the world. But it does lead to risks of overexploitation, especially in the scallop. It's been seen in sedentary species, I should say, rather than the scallop. And there's numerous examples of failed fisheries management. Serial depletion is a classic where you fish a bed, everything looks great until the bed's empty. And if that's the last scallop bed there is, because you've done this serially over the course of your fishery, you have a serial depletion problem, and you may not even notice it until the last minute. The heterogeneity can cause challenges in estimating abundance and biomass. If you don't carefully lay out your survey, you can end up having that survey in a bed, sampling very heavily in that bed, and all of a sudden you think there's a lot more scallop than there actually is. And all this can lead to misperceptions of the stock status. So transition now to kind of the fishery we have in our region. So this is the second largest fishery in the Maritimes region. The price of scallops has gone through the roof recently. And so there's a lot of money to be had in this one. It's two components to it. There's an inshore and an offshore fishery. Georges Bank down here is really the main, I mean, of all of it, most of the scallop in the Maritime region comes from Georges Bank. There's about 4,000 tons typically come off this bank in a year. But there are other offshore banks, Browns Bank North here, this is Sable Bank, Bank Row, and the Maritimes region is allowed to fish part of St. Pierre Bank as well. We won't talk much about the offshore fishery, really, nothing more, because all of our modeling work we've had Raphael do is focused on the inshore fishery. And primarily this is the Bay of Fundy, so that's where the vast majority of this component of the fishery is, but there are other areas right along the coast of Nova Scotia where there is a fishery outside of Bay of Fundy. Management, so this is a zoom in of the Bay of Fundy, and the management of the Bay of Fundy is pretty complex. Not all of these, but a lot of these sub areas are actually assessed on their own. They're all TAC-based fisheries in the regions we assess, but a lot of small management areas. And the advantage of this, and history of this, is really this functionally controls local exploitation. So that I have this little area here called SPA4 is its own assessment, and then this area over here, SPA3, is its own assessment. That helps us determine, okay, we want to keep this healthy and we want to keep this healthy. Whereas if we had just had a survey of the whole thing and done an assessment on the whole thing, we may end up with that serial depletion problem where you can deplete this area without really noticing that you are. So really does help us control local exploitation in a world pre-spatial assessment. But the downside for us is this is really in a resource intensive, and by resource I generally mean human resources, assessment process. So we assess it by management unit, which means we have 9 independent stock assessment models just for this area, and we have to assess each one of those, and TAC decisions are made on each one of those. The other downside of this is getting a holistic understanding of the status of the stock in this complex is complex. It's difficult because I may have this 2 areas that are healthy, but then if I have an area over here and an area over here that are in the critical zone, for example, is the status of this stock healthy? Is it cautious? Is it critical? So it's hard to know, writ large, what the overall patterns are in terms of health. But again, it does help us on a piecemeal basis to understand. So our existing stock assessment framework, I mentioned Stephen's name earlier. So Stephen Smith is really the father of our models. He developed this about 20 years ago, which is really cutting edge. It was a Bayesian state space modeling framework. I think 2002 it came out. There weren't many people doing that at that time. Over time, we've applied the model to more and more areas. So as I say, we now have 9 areas and 9 models. So we started out with 1 and we've kept adding as time goes on. They're all based on a biomass dynamics model, and I'll explain kind of what that means in a second. It's kind of just accounting when you get down to the nuts and bolts of it. And about 10 years ago, reference points were developed for all of these areas. Starting 10 years ago, reference points were developed for all these areas. Some are more recent than others. So our existing stock assessment model, we have our biomass in year T, right? So that's what we're generally really interested in. Commercial catch is removed from last year's biomass. So that happens first. Then they die through natural mortality. And again, we have that Clapper equation. And so these are our outputs or our removals, better word for it, right? So we have natural mortality shrinks our population, commercial catch will shrink our population. Our population will grow from just natural growth of the individuals. So this is a scallop next year is going to be bigger than a scallop this year. And recruitment. So we actually have a really good recruitment index, which is nice, and another feature of this system that is challenging for a lot of fisheries. And the last thing I'll mention is this temporal error term. And I only mention it because Raphael is going to hammer on this in his parts. So he's going to discuss, at least he was in the last version I saw. I should say Raph, I shouldn't say yeah. But at this point, it's just temporal error. So every year we have uncertainty there. Yeah. And so I say about 2014, 2015, I would say 2014 actually, it was just before I had started. There was a push to reformulate and look at the stock assessment model in a frequentist framework. And what this process found was there's challenges with identifiability and estimability in a statistical sense of our model parameters. And the issue really came down to, we have a whole lot of what are known as priors. So this is in our Bayesian model, and these priors, if you don't know, I mean, the easiest way to say it is we have a parameter and we don't know what that parameter is, and we put an initial guess on that. And we had done that for dozens of different parameters. And any one, let's say catchability, I said, I wasn't sure what catchability is, but I guessed it was between 0.2, 0.5. I put a prior on that. But then I also had priors on natural mortality, and I had priors on a whole lot of different terms. And what that really did was constrain the model far more than we thought it was. And the combination of all these priors was quite informative. And it could lead to unexpected consequences in our results. This frequentism version of the model that Yihao Yin came up with, it was published in 2019, but I'd say 2017, I think I saw it first. The model now was identifiable with the changes he made with it, and the parameters were actually quite well estimated when he did the simulation work. Then we used this in a case study in SPA4, it's called, one of the areas that we tested. And the model results for that area were quite reasonable. Biomass estimates were a bit lower. It was really driven by a change in the catchability estimate from the model. And we had far fewer assumptions underlying the model. So we were able to recreate patterns that we saw in our Bayesian model, which was good. Yeah, and in theory, we thought this might be a new way to provide advice. Then we tested it in other areas. So we used GHAV's models in other places, and the results really were all over the place. I had one small population that had a pretty much infinite biomass. It was the catchability, biomass, and mortality estimates were often very unrealistic when we ran this model. So we went, oh, hold up, okay, we need to go revisit this. And this is kind of where RAF comes into the picture. We said we can't operationalize, we can't use this model for assessment as it is. So, but we thought it was a promising path. It definitely, there were some useful pieces to it. So we identified that we needed to generalize this model. So we've developed at this point 3 models with increasing complexity. First one is this integrated TLM model. And essentially, instead of having one biomass estimate for this whole area, we use the data in a more raw format. So the actual survey toes inform the model rather than trying to get an estimate of the survey and putting one number into a model. Then RAF expanded on this, and we get developed the spatial temporal, the SEBDAM model that I mentioned before, and Raph will show you a little bit in TEAS on their spatial temporal plus habitat model. And this is thanks to Craig Brown and Brittany Wilson and others who have mapped and given us bottom a bentoscape map and habitat suitability map for the Bay of Fundy at this point. So still under development, but we do have some initial results from it. So I will shut up here, and Raph, you can take over, and I'll stop sharing.
We're gonna hope this works. Can you see my screen? Dave's giving me a thumbs up, so I'm gonna go with yes. All right, cool. So hello, everyone. I'm gonna start with the first step of our model development that we did, which was the creation of the TLM, which just stands for tow level model. So the original conceptualization for this model and what I was trying to get for this was basically as an in-between between traditional approaches to stock assessment model, where like Dave said, you just have a single index of abundance that you've obtained in some ways from a bunch of observations in a given year that you then use to feed your stock assessment model to get your population estimate. But it's also between a fully spatiotemporal model wherein each survey tow individually is important because it's their location that you use to inform the estimate of population abundance / biomass. So starting from the beginning, how exactly do we traditionally calculate survey indices? Usually just get them by aggregating over your observations, whether that's through stratification methods or modeling methods or just taking a straight mean for some reason. Unfortunately, some information is often lost in this type of aggregation process, and it's also very difficult to appropriately propagate the uncertainties from your original data to your model output, because these indices obtained from these observations are usually, from the perspective of the stock assessment model, they're usually just treated as raw data. That's how it sees it, even though there's a whole modeling or stratification process that goes into it beforehand. So our thought in creating TLM was, what if we skip this index middleman and we didn't aggregate tows before fitting them to the stock assessment model? So just as a quick summary or refresher for stock assessment people, this is what a more traditional stock assessment observation equation will look like. So you'll have your observations on the left that you then aggregate into some way, like I said, using stratification or some model to get an index of abundance. And then you take that index and feed it to the model on the right that will then get you a population estimate in some way. And then the actual observation that the model does usually looks something like the equation at the bottom, where you have IT, which is your index of abundance in year T, that is related to the biomass B in that year through a catchability parameter, and then some error term to account for your uncertainty in your observations. Now, this can absolutely work, but it does make it more difficult, as I said, to propagate your uncertainties forward from your observations to the index, through the index to the actual model output. Now, if we want to model the tow level data directly in the stock assessment model, this does require modifying your traditional equation, and mostly because you need to account for features of the raw data that a stock assessment model usually can't deal with, such as zero inflation and other factors like this. But if we do this, this then allows us to, as I like to say, skip the middleman and feed your observations directly to your stock assessment model. So what I did is pretty much just modify the equation where you add a subscript I to on the left side of your equation. So it would be your index from a given tow I in year T, and then you have the equivalent subscript I on your error term, as each individual tow now will have some uncertainty and some error term associated with it. And then we also decided to implement a delta model, wherein your probability of encounter is modeled using a binomial distribution based on the number of positive tows, which will get you your probability of encounter down here, and which will allow you to deal with basically excess zeros. And what this equation implicitly assumes is that each observation is an independent replicate observation of your underlying biomass BT, because there's still only one biomass in a given year, which is the thing that we're actually interested in, while accounting for the impact of empty tows and or zeros. Now, We first tested this approach in the SPA3, so the Scallop Production Area 3, which is on the western coast of Nova Scotia in and around St. Mary's Bay. And if you're curious, because obviously I'm skipping over a lot of detail in the interest of time, but we published this work in fisheries research early this year. But basically doing this, it allows us to directly use the tow data without having to obtain a preliminary index. It allows us to do all of this while still having fewer assumptions than the currently operationalized Bayesian model. And it reduced the uncertainty around your final biomass predictions while improving your error propagation from the raw data directly to the final model output, meaning that those uncertainties that you get, as you see on the right, are more reliable than they would be when you just have an index. I don't think I pointed it out, but in red was the operationalized Bayesian model, and in blue was our approach using TLM. Lastly, and for our purpose here, probably most importantly, directly using the raw data in a stock assessment model allows us to much more easily move towards explicitly modeling the spatial population dynamics. Sorry. And this is because, while we don't personally aggregate the observations before feeding them to the stock assessment model, the model itself still aggregates over space, even if that information that's present in the data and its uncertainty is more appropriately propagated forward. But because we have each individual tow in there, that means we have the location of each individual tow. And that allows us to incorporate that spatial variability by the use of spatial statistics or geostatistics in our case. And while there's a lot of different approaches or methods you could use, we chose to use Gaussian Markov random field. Now, I'm sure some people are asking, what does that mean? So a Gaussian Markov random field, or a GMRF, I'm going to do my best to explain it in overly simplistic terms. So imagine that you have some given area, the field, and you have a bunch of observations that are spread across that area. Then you would make the assumption that this field, so the spatial distribution that underlies your observation, are normally distributed, meaning that it follows a Gaussian distribution. And then furthermore, you add in a Markov property, which basically means that if you take any point in the field, its direct neighbors can help explain its specific value. And this Markov assumption is key for the creation of sparse matrices that will make GMRFs incredibly computationally efficient, which is very important. Because if you can model like just a GRF, so without the Markov property, but it makes your covariance matrices very large and it's incredibly computationally expensive. Furthermore, to get these GMRFs going, you do require some assumption as to how these points are correlated to one another across space to get your covariance matrix for your random field. The correlation structure we chose to use, which is also the one that's probably the most commonly used in fisheries at least, is the Matern correlation function. And you can use this function to estimate how points are correlated to one another by the distance between them. And at which distance do two arbitrarily chosen points stop being correlated? Anyways, now moving on to our spatially explicit biomass dynamics assessment model, or SEBDAM, because I thought that what's the point of creating model if I can't make up a convoluted acronym for it? I turned my attention to the process equation, as TLM mostly focused on the observation equation. Mostly because conceptually it made more sense to us that it was the underlying biomass itself that was spatially correlated across space, and it wasn't necessarily the survey itself. So what we did was basically start by adding the subscript S for the location of the knots. I'm going to explain what knots are in a second. But basically S for the location, to the biomass, to the mortality, to the commercial landings, which basically means that we can have different landings in different areas, which is very useful for fisheries where fishing intensity is very spatially aggregated, to the recruitment. And then this is what Dave was pointing out towards, is we replace the original log normal error term by a Gaussian Markov random field with mean zero. And this allows the biomass at each knot to be correlated through space. And the idea behind that is that this will soak up the latent spatial patterns that are present in your data. And as you can implicitly see from this, we also made natural mortality and recruitment spatial. They used to just be random walks across time, and we made them spatial temporal random walks in a similar way as that we changed their residual structure to be explicitly spatial, or spatial temporal. Now, what are knots? This is always fun to explain because it took me a long time to figure this to truly understanding. But when you're doing geostatistics or spatial statistics, what you're focused on is modeling the location of each individual observations. As our surveys use stratified random sampling designs, those locations change every year, as you can see in the figure on the right with 2 randomly chosen years. And this makes it a bit more complicated to conceptualize how you would move the biomass through time, because if think of it this way, if you move the biomass like at a given toe through time, how do you directly relate that biomass at that specific location to the next year's biomass when you don't have this specific location, and you might never have the specific location surveyed ever again, just because of how stratified random sampling design works. And furthermore, while there are ways, and I've thought about how to do that, they are also incredibly computationally expensive. So instead, what we chose to use is a predictive approach that utilizes knots. And if anyone here is familiar with the VAS model from Jim Thorson, this is also at least what he used to do. I haven't looked at it very recently. Sorry. So what this means is that the biomass is exclusively modeled at knots and not at each individual location, which means that it's the location of the knots that are used in the spatial component of our model. You start by choosing a number of knot, which is chosen by the user, so in this case, me, and you have a trade-off where the more knots you have, the higher the precision of your model, but the higher the computational load. So you find a good in-between between your computational power and how precise you need to be. And then what you do is you take all of your survey toes across all years, which is what I'm showing on the right, and then you use a clustering algorithm based on to get the location of your knots, which show up in black here. And it's at those knots, so at those black points, that I will be actively modeling the biomass itself. Yeah, and then the last thing you do is that you assign each of your survey observation to the closest knot, which basically means that each knot has like replicate observation of the underlying biomass at that knot. And what this allows us to do is to have an uneven grid, because each knot can cover different area sizes, and if your survey is more aggregated, you'll have smaller knots that cover smaller areas, and in the areas with a higher survey coverage and all that. In our case, it wasn't a massive difference, but it's still an uneven grid. But because each knot covers different area, we thought it made more sense to model the biomass density instead of the total biomass, as that would ensure that everything is on the same scale and therefore directly comparable. And since you're modeling the biomass density, you can always later scale back up to represent the whole area. Now, we also fit this to SBA3, so the same area we did our TLM work earlier. And the results that came out of this were very interesting. Yeah, because they allow us to basically better capture and take a better look at the information that is present in the data. And that information that can be like incredibly important about whatever species you're looking at the time. In our case, with the scallops, SebDam was able to identify like fine scale time varying spatial patterns of biomass, of recruitment, and of natural mortality, which is what I'm showing at the bottom. I just chose a few random years where you could see a difference, where early in the early 2000s, you would see some trends in these, and in the mid 2010s, you'd see that pattern has pretty drastically changed in a lot of these. Yeah, so basically this allows us to track both the overall population trend, but also the localized shifts in productivity, which also includes spatial shifts in fishing effort, as because all of your commercial landings are also attributed to each knot, which means each knot can have different fishing intensity. And it allows us to capture the underlying spatial patterns without having to explicitly model or even know what the mechanistic processes are. However, what this does allow us to do is to make informed hypotheses about what kind of processes could potentially explain the patterns that we are seeing here. And I want to give a specific case for this, where if you look here, this figure basically shows how far do 2 points need to be in all directions to stop being correlated? Yeah, and what you can see is that the biomass is correlated at much larger distances on the north-south axis than on the east-west axis. And if you compare that to what we know of this environment, you can see that on the average in this area, if you're going west from the shore, the further you are from the shore, the deeper the environment becomes, which is interesting and could potentially be part of the explanation as to what's happening here. We also know that the north-south axis follows the tidal flow in and out of the Bay of Fundy itself, which could also potentially be impacting the population. As I said, this isn't objective proof, but this allows us to look at potential patterns related to the environment, to what we know of the environment. Now, another advantage of going spatial or spatial temporal is that if you compare it to more traditional assessment methods, and I'm sure this will be familiar to fisheries people, you can have a few particularly influential tows, which are usually tows with crazy high catches compared to everything else. And those can end up driving your index in a given year. And while other methods like modeling or stratification methods definitely do help, there's a lot of times where these indices will remain overweighed, quote unquote, by these tows. In a spatially explicit model, you kind of avoid these disproportional impact, but you still retain the important information that is present in those tows, and that does represent reality. So just as an example here, I was looking at natural mortality for this area, and in black/gray, you have the output from the temporal model, so TLM, and in red, you have the average natural mortality from the spatially explicit model, so SEPDAM. Sorry. Yeah, so if you look at here in 2013, you can tell that both models are basically predicting that the average natural mortality is the same. And if you look at it spatially, you can see that that isn't that surprising, because while there are differences across space, they're not crazy large differences. Like the knots with higher mortality are not that much higher than the knots with lower mortality. But then if you move and you look in 2002, where there's a notable difference between what the temporal model and what the spatial temporal model thinks, you can see what's happening. It's that there was a localized, a very high mortality event that happened on the outskirts of the area. Sorry. But that event was very localized. And the spatial temporal model still accounts for it. It's still happening, but it is restraining it to the actual part of the population to which it happened. So basically, this mortality event did happen and does need to be accounted for, but it is not necessarily representative of the entire population, as the temporal model basically has to think. It doesn't really have a choice. Yeah, so lastly, not only do we get all the spatial information that previous approaches couldn't give us, but we also obtain prediction of the total biomass in the area, which ends up having lower uncertainty around its point prediction than the temporal model. As you can see here, as before, gray is TLM and red is SEPDAM, so the spatially explicit model. And this reduced uncertainty can then be directly translated into reduced risk in the science advice that is provided to fisheries managers. So to recap, Going Spatial provides us with a lot of benefits, from reducing uncertainty in parameter estimates, from better capturing the underlying population dynamics of our studied population, from giving us the ability to track spatial productivity shifts, and finally, it also enables the simultaneous modeling of the entire area or a subset of it, meaning that from a management perspective, you can also just subset from the total area that was modeled to fit your current management needs or your current management areas, and still have the real model uncertainty in this area. And this does not require you to make the assumption that your populations across management lines are not connected at all, which is an assumption that is very rarely respected in real life in my experience. Now, obviously, there's a lot more detail about this that I didn't have time to cover here because it would be here for 3 days. But if you are curious and you want to read more about it, this was published late last year in the IC's Journal of Marine Science. And also, you can always just reach out to me about questions. I love talking. I'm sure that's no surprise. Now, my original hope here was to go into details about the work that I've been working on in the past months and that I've started to show preliminary results. But we thought that maybe 70 slides was a bit much, especially since I feel like I've already thrown a lot of information at all of you. So instead, I'm just going to give a sneak peek as to what we've been up to and what those preliminary results look like. So a key part of what we were aiming to do with these two models was to maximize the amount of information that you can get out of your data, of your survey observations, and try to implicitly capture the underlying impact of the environment, but without actually incorporating those environmental variables inside the model. But I'm sure this will surprise no one, we could probably incorporate these environmental covariates and see some improvements in what we are getting out of the model, which is what we have currently been looking for. And more specifically, as Dave pointed out earlier, we have been looking at how to incorporate basically habitat suitability into our spatiotemporal stock assessment model, moving into the actual Bay of Fundy itself instead of just one small area. And unsurprisingly, and even less surprisingly, if you think specifically about scallops or bottom-dwelling animals that don't tend to move a lot, bottom type is often a pretty good proxy for the suitability or the quality of habitat for these animals. And I put at the bottom right here a picture of most of the dominant bottom types that you can find in the Bay of Fundy. Yeah, and this is because sediment type has been found to be highly important for like scallop settling, and I don't mean settling just in juveniles or in larvae attaching themselves, but literally just for larger animals, because as the older the scallops get, the less they tend to move, and they tend to aggregate into the better environments and then don't move a whole lot once they get there. Yeah, and then furthermore, if we started by just subsetting the data we have by these habitat types to see what it looks like. And there are very clear differences, even in our survey, which wasn't built to find those things, but just by subsetting by these habitat types, we can find clear differences. And there are also differences in fishing effort, which is the figure I'm showing at the bottom here. So on the y-axis, what we have is the number of like fishing records per kilometer squared of that specific bottom type. And you can clearly see that the fishery tends to mostly ignore some areas and very heavily focus on other areas, which makes sense because not only, I mean, there is literature and we can visually see that when we look at it, but the fishery will tend to focus on the more productive areas and areas where they get more for their time and effort, which makes a lot of sense. But when we looked at the actual survey data itself, we also saw a very notable difference for the animals themselves, where like for some sediment types, which are usually finer ones like silt, they tend to have more clappers, which usually means higher mortality, and they tend to have fewer recruits and have fewer commercial size animal. And you see the exact opposite trend when you look at coarser sediments, so gravelly sand or mixed sediments. And unsurprisingly, these are the ones that they tend to focus, that the fishery tends to focus more on. Yeah, so basically our aim in the current work we're doing is to inform the model structure itself using this information. This was done mostly by modifying how we incorporate zeros and empty toes in the observation equation, mostly focusing on using negative binomial models instead of just binomial. Sorry. We also modified how we estimate our catchabilities, and we've used it to inform our modeling bounds. And all of this has been pretty successful in fitting this new habitat-based model to the data from the Bay of Fundy, which also allows us to look at as to what happens when you fit one model to multiple management area, because we're covering at least 3 with this. And then I wanted to just give a sneak peek as to what these output looks like. So if you look on the right, this big figure is the predicted commercial biomass density across most of the Bay of Fundy. And you can see that some areas are pretty consistently low density, usually more on the eastern edge. And if you compare that to this figure here, which is the bottom types across the bay, you can see that that kind of matches up with this figure, with this color, which is sand, which is interesting. And what I think is super cool too is that you can really clearly see a shift as to what's happening to the population over time on the western edge of the modeled area, so down here. And you can see, yeah, So even from the current assessment, the peak of the landings and the population was in the early 2000s, and you can pretty clearly see why, because you have this massive spike in biomass density in the early 2000s. Yeah, but this was very highly localized. What's interesting is that later on, so since the mid 2000s on the western edge still, the model says that if you look at the population overall, so the total biomass, it's actually at similar levels than the early 2000s. But you can also see that it's a lot more spread out than it was in the early 2000s. And that has very interesting implications for your perception of the stock, because from the fisheries perspective, this meant a lot more scallops for lower effort, while this, even if the overall population is at a similar level than it was early there, they still have to put a lot more effort to get the same amount of biomass out of the water. And that can definitely influence your perception of it. And it's still something, obviously this is still under development, but it's something that I'm very interested in looking at. And furthermore, and that's what you can see on the left there, is that we can use those bottom types to help get us basically spatial catchabilities, where you can have a different catchability at every knot based on what the underlying bottom type is and based on what we expect the gear efficiency to be based on the literature and what we know of the sediments in those areas. Yeah, so that was the quick sneak peek that I wanted to show. And to conclude all of this, it's very important to remember that spatial patterns are a proxy for underlying ecological or environmental processes, and that recent advances in both computational and statistical methods have enabled us to incorporate these patterns into our model. Our spatial temporal and habitat-based approaches allow us to better leverage the information that's already present in the data, and it helps us account for spatial dynamics within the precautionary approach. Most importantly, and that's what I want to leave us on, is that our aim is really to maximize the information that we can extract from the data to find the signal that's in all the noise. And I want to thank a great many people who have collaborated with us, too many to name every individual, but I wanted to specifically thank Joanna Mills-Fleming, who is my co-supervisor at Dalhousie Statistic. I wanted to also thank Craig Brown at Dalhousie, Jessica Samioto at DFO, and Brittany Wilson at DFO. We also wanted to thank our partners in the OFI benthic Ecosystem Mapping and Engagement Project, with whom we're currently collaborating on our current model development, and all our partners at DFO, NARCAN, NSCC, UNB, Acadia, and our industry partners. So happy to take questions now. Thank you.
All right, thank you. Yeah, so if we have any questions, you can type it in the chat and I'll read it, or you can raise your hand and I will call on you.
I hope I didn't speak too quickly. I tend to speak fast when I present, and I apologize if it was too quick.
I have a question about the clappers. That's what that's what I was mostly intrigued by. First of all, how long does it take them to separate? Do you know that? Like, just like how useful, if you catch them, are they together the last 6 months? Did it just die a year ago, 2 years ago, 5 years ago?
I think you should start, and I'll finish.
Okay, I'll take that one. Okay, sounds good. It varies by bottom type. There's been some discussion that they may, if there's heavy fishing in the area, that would break them up more quickly because it's just they're getting disturbed more often. It's in the few months range. I think that's generally how we think of it. And in our old model formulation, we kind of had this dissolution index, which gave an estimate of how quickly they'd separate. But most of the literature I've seen, it's from a couple months to 6 months. I don't think it's
Okay.
much more than that.
Okay.
I also wanted to throw in there that the way we incorporate natural mortality is an instantaneous natural mortality and not like directly. Yeah.
I was also curious about so you were talking about you do incorporating natural mortality, but spatially, right? Like, so it could be different per unit. But so how much does the current affect how, like, do the clappers, do they move, or do they mostly just stay still when they're dead? Because I imagine, they're not. they don't have any control over that. So
That's a good question. I've never even thought of that one before, to be perfectly honest. I don't think they'd move far because they'd be in a bed, and hydrodynamically, I think it's, reasonably benign area. But I mean, in the Bay of Fundy, we got some crazy currents, right? Um, I would think that would probably a stronger current. The biggest thing would probably break them apart, right? The more they move, the quicker they're going to fall apart on us. It's certainly not a perfect index, but it's neat that we have it.
yeah, it is really neat. I was just thinking about when you said that you mostly found clappers in one area. I was like,
Yeah,
well, are they just kind of like funneling into that
aggregating.
area
Yeah.
from nearby areas, even if they only
The
move like a little
The
bit?
neat, yeah, the neat thing about what Raph found with that is the areas where he is seeing that are the areas on the edges generally.
Yeah,
Usually the
it's
highest.
basically in both SP3 and like the Bay of Fundy, the places with the highest natural mortality are the places right like at the transition zones between different between different sediment types, with the like garbage sediment types for scallops like right
Yeah,
next to it.
yeah, neat. Oh, well, we got some hands. All right, I'm just gonna go in order. Sherry Lynn.
Okay, thanks, Colin, and thanks, David and Raphael, for a great presentation. I'm not sure if you had an opportunity to meet Stephen Smith before he passed away, but I had the great pleasure of working with him for a number of years on this particular assessment, and I think it's safe to say he would be very excited and pleased with the work that you've done here so far. So congratulations, and thank you for carrying on his legacy. It's really nice to see.
Yeah,
Thank you.
A quick question. You mentioned, and it's really interesting to see what you've done with this particular assessment. But with the spatial modeling approach that you've taken, you mentioned that one issue related to having a stratified random survey design, and you had to take this knot-based approach, I guess, for dealing with that. As I recall, in some areas, particularly SPA 6 at one point, they were actually using a fixed survey location approach. How, I'm not sure if that's still in place, but like, how might that work here? Would there be benefits to maybe looking at the survey design more generally, or like, do you think this current approach that you have is sort of covering it? I'd be curious to get your thoughts on that.
I think that, and this is partially I've been doing separate work looking at spatial models. There are different models about halibut, but I've been looking a lot about like the effect of fixation, and I think fixation is almost strictly worse for this type of model because like the spatial approaches do assume they assume that there's an equal probability of you picking any point, which a fixation would absolutely like violate those assumptions. And there's a higher chance, especially the problem with fixation, in my opinion, is that they can be very good, but if you ever see shifts in like spatial shifts in the population you're looking at, fixation have a way higher probability than a stratified sampling design to miss it. And even using spatial methods will not help you with that because it's going to be, your data is going to be biased basically. And if your data is biased, there's only so much you can do. I hope that answered the question.
and I think to add to that, Raph, I mean, we've talked a lot about this, and I think before your halibut stuff, we weren't sure what the actual answer was to that. And our strata, I mean, strata, Sherilyn, but I mean, they're set up to be homogeneous areas, and that's kind of, it's almost irrelevant now to us. But I think the key is to still be randomly sampling across your whole domain.
Mhm.
Whether you need to spend a lot of time thinking about the stratification of that, I'm not sure yet. I'm hoping Jim Thorson is working on this somewhere because it's a really interesting question to me of what we need to do for stratification. And thank you for the Stephen shout out. I mean, all this was
Yes.
Stephen's idea. This is us hopping on his coattails. Jessica started it. Joanna was working with Steve. Joanna Mills Fleming was working with Stephen. And then me and Raph kind of showed up over time and jumped on this. Really, it's a cool idea. And I think we're making some progress with it, which is nice.
Yeah, that's great, and that response certainly makes sense. So so thank you kindly.
All right, Arnaud.
Hi, thanks for nice presentation. Question. So you went a bit quickly on the last part, which is how you incorporated, habitat type into your observation model. Could you just elaborate a little bit on that? So I assume, are you affecting like the probability of presence based on the habitat type, or what's roughly like? Could you just elaborate a little bit on that?
Yeah, sure. Are you mostly focused on the on like the probability of zeros, basically?
Well, so I was thinking, yeah, I mean, I was trying to understand how you incorporated habitat type, because this is the work
Yeah.
you're doing.
Yeah.
Based on
So for probability of encounter, it's the traditional approach is the delta model, where you just use a binomial distribution that's based on like the number of positive toes versus the number of all toes, and then you get a probability of encounter generally. What I've done is basically replace that with a negative binomial approach that models directly the number of scallops we catch instead of the number of positive toes. So like within each toe, I look at how many scallops we're catching, and then this allows me, I can basically have a different zero inflation parameter by habitat type. So I basically have a negative binomial that models the number of scallops that are caught in a toe, and then I can have a zero inflation model added to it. It's basically just a zero inflated negative binomial model that replaces this section, if that makes sense.
Okay, so I guess you estimate but are you informing that zero inflation are you informing the negative binomial model by the habitat type? Like, do you have directly?
I am not informing it. It's different parameter by habitat. So basically, each toe will have a habitat type associated with it, and then it looks at it separately by habitat type. So it basically assumes there's an independent zero inflation parameter depending on your habitat.
Okay, perfect. Thanks.
All right, Noel.
Okay, thanks. My camera on? I don't know. Maybe not. Stop that. Anyway, I was trying to turn my camera on, but I don't think I was successful. So the model is so it's a spatial model, so it's a kind of more high resolution in the spatial dimension. I'm wondering if you've thought about increasing resolution in the temporal dimension. And so I guess the first question would be, like, how long does in a typical year, how long does the scallop fishery go for? Is it just like, just a week and it's done, or is it several weeks or a couple of months, or what's going on there?
Dave, do you want to take that, or I take it?
I can start it. Well, you're setting up my 20-year goal plan of having a temporal spatial model where we can actually do this by kind of month. But it depends on the area. So like offshore, it's a year-round fishery with peaks through the season. In Bay of Fundy, there's definitely seasons, and it depends on the area you're looking at. The areas RAP's model right now has a general season, and they kind of start, I think it's mostly in October, and Jessica can correct me if I'm saying anything totally out to lunch here, but it's mostly in the fall through the winter and spring is when most of that fishery happens, and then turns off. We don't have a lot of good information for inshore on, what's happening outside of our survey window and kind of that fishery. But offshore, we actually have some really neat data that I think we could start to address a finer temporal scale, but that's down the road yet, but it's definitely in the back of my head.
Yeah,
So
does this, oh, sorry.
yeah, so what I'm thinking about is, would there be evidence of local depletion if you start looking at well, you have it spatial, so if you started looking at the effective catches on scallop population sizes at a finer resolution, you possibly anyway, you may start picking up on some spatial depletion signals that could improve your biomass estimation.
Yeah, man, I mean, we have such good resolution data for sure. Raph, you got to throw in your fisheries rant now.
My catchability rant, which
Your
I have a
no,
lot
no,
of
not
rants.
that one. No, your fisheries one from the first paper where we talk about how the
Oh,
fishery
that one.
spatially exploits the population, because it's really neat issue you came
Well,
up with.
yeah, because I did a lot of simulations when I created the spatial temporal model about looking at like if you have a highly aggregated fishery, what does that do to a temporal model? So basically simulating biomass and catch from a spatial temporal model, and then scaling all that data and then fitting it to a temporal model. And I basically, no matter what I did, there was always bias in the temporal model, which I'm not entirely sure what that means because I need to do more work to figure that out. But like a spatial fishery does something to your model that from my simulations, my spatial temporal model seemed to be able to capture that, but that was at the resolution I tested it. And I could probably test it at a finer resolution. A very fine resolution is hard with these because they're a hierarchical model and the spatial component is at it's at the process equation, so it's the lower level. You need more data than if I'd put the spatial structure on the observations itself. So I can only go so far in high resolution. I have no idea if I answered the question anymore. Sorry.
I think about that. I mean, we can get to there's a limit to how resolved we can get. We can't get to the bed level for most beds, but we could get an area and see local depletion within an area for sure with what we have, if we could get a little better temporal footprint there. But it's at the scale of a knot, right? I mean, basically we've changed from the scale of a whole area to the scale of a knot. So we can see things at the scale of a knot, I think.
All right. Sherilyn, did you have another question, or is your hand just still up? Okay. All right. Are there any more questions? I think Carl would have been happy with what you guys have
There's
done.
DFO and math. Thank you. I was hoping for that joke somewhere. Some DFO can do math with their students. Anyway, there is occasionally still some. That was very entertaining talk last week from Carl.
Oh, it was hilarious. It was hilarious.
That was prime Carl right there.
I was looking, like I told you guys before, I was just looking through the participants list, just like, oh my gosh, they work for DFO, they work for DFO, they work for DFO. Oh my gosh.
You get a thick skin, Colin, don't worry.
Yeah, I imagine.
I'm probably not allowed to publicly say I agree with some of the things Carl said, so I won't, but
Yeah. All right. Well, I think that's it for questions. Before I end it, I do want to say I want to introduce next week's seminar, and it's the final one for winter 2022 for MIGS. Dr. Vincent LaCours from the University of Florida will be giving a talk titled Ocean Mapping, Considerations for Data Characteristics. So yeah, thank you guys. Thank you guys for your presentation. That was a blast from the past for me and way over my head at the same time, but I had to follow along a little bit. So anyway, yeah, thank you guys. That was great.
Thank you for having us.
Thanks everybody. Yeah, it was good. Thanks.
Thank you everyone.